Okay, we're going to be looking at lots of integrals and working through them. And our first segment here is we're identifying the techniques that we'll use to do the integrations. And in some cases, we will be using multiple techniques to solve a single integral. So, listing them out, the first one will be division. And that would be something of this nature. And we would carry out the division and then term by term we will be able to do an integration. Our second method, and we've seen most of these methods already, partial fractions. And the partial fractions start out with an integrand of this nature, and we can break that apart where we could say c to the 1 minus x squared is equal to a 1 plus x plus b 1 minus x, and then we would multiply across. We've got c equals a 1 minus x plus b 1 plus x, and then we'd solve for a and b and integrate individual terms. Our third method is integration by parts. We've seen that, we've done that, and that one is uv equals u dv plus v du. Our fourth method is simply a u substitution. Where we have u equals some more complex polynomial, and then du equals 2 dx, and we would put that back into the integral, and because of the simplification, we're allowed to, it enables us to take the integral, calculate the integral. The last one is one we haven't seen so much yet, trigonometric substitution. And that's where we have, let's say, an integrand 1 minus x squared, and we say x equals sine theta, and dx equals cos theta d theta. And then we would end up with something like this. And then we know from trigonometric identities that this is cos squared theta, so we have secant theta d theta, which is 1 over cosine theta. And then we would go through our process of solving that. So we're going to use all of these techniques in the following couple hundred integrals. We're going to just solve tons and tons of integrals, and we'll use these techniques. So let's get started. Now, before I get going, I'm going to have to find our starting point here. I got a ton of integrals. All right, let's get started with this one. Now, in this case, we would basically just break up the integral into 2 separate parts. We wouldn't try a substitution here. We would just go x over x squared plus 2 dx plus dx over x squared plus 2. Now, in the first integral, we would use a u substitution. So here we'd say u equals x squared plus 2, and du equals 2x dx, and du on 2 equals x dx. So now that gives us a familiar form. That gives us 1/2 du on u. And then on this one, this integral, the second integral, we will need a trigonometric substitution. So let's try. This is where it gets tricky. We have to kind of use an educated guess. We rely heavily on trigonometric identities, especially the cosine squared theta plus sine squared theta equals 1, and the variance, which is 1 plus tangent squared theta equals secant squared theta. So in this case, we're going to use, because we got a plus sign in the denominator, we're going to use the x equals square root of 2 tangent theta. And then dx equals the square root of 2 secant squared theta d theta. And we make our substitution. So we got 1/2 du on u plus, now in the numerator we have square root of 2 secant squared theta d theta, and in the denominator we have 2 tangent squared theta plus 2. And we can bring that square root of 2 over 2 out. And we recognize that tangent squared plus 1 is secant squared. So here we have 1/2 du on u plus square root of 2 on 2 secant squared theta d theta on secant squared theta. Those cancel, and we have now 1/2 ln u plus square root of 2 on 2 d theta, and that's equal to theta. So we have 1/2 ln u square root of 2 on 2 theta, and of course we got a constant. And now we got to substitute back in for theta. So we had used x equals square root of 2 tan theta. So if we have x on the square root of 2 equals tangent theta, we can just do the arctan of x on the square root of 2 equals theta. So our final solution is, well, it's not final yet, ln u, but u is x squared plus 2 plus square root of 2 on 2 arctan of x on the square root of 2 plus c. And so now we could use some exponent or natural log properties, characteristics, and get rid of that 1/2. So what we could do is we can write this integral x plus 1 over x squared plus 2 dx, and that's equal to the natural log of the square root of x squared plus 2 plus square root of 2 on 2 arctan of x on the square root of 2 plus a constant. And there we have it. Now, we use two different techniques. in solving this integral, we use the U substitution for the first integral, and we use the trigonometric substitution for the second integral. And basically, we didn't try to solve the integral on its own. We broke it up into two parts. And then each part we used a different method for substitution. Now, we're going to look at a similar problem. Let's take a look here. Okay. We're going to take a look at this one. This one's a little simpler, actually. We got x on x squared plus 3 dx. Here we use a u substitution. So we go u equals x squared plus 3, and du equals 2x dx. And so we have 1/2 du equals x dx. And now we have our familiar form. We can bring out the 1/2 du on u, and that is simply 1/2 the natural log of u plus c. And now we plug back in the original x squared plus 3 plus c. And we could take it one more step and go natural log the square root of x squared plus 3 plus c. So this integral is equal to that solution. Now, in this natural log, we had the 1/2 ln x squared plus 3. Now, we realize using, let's say, y equals that, we know that this is really an exponent, so that equals ln of x squared plus 3 to the 1/2 power. But that's equal to the natural log of the square root of x squared plus 3. So if you're wondering where this came from, it's just a characteristic or property of logs. That was a pretty quick one. Like I say, we have well over 200 integrals solved. Now we're going to take a look at where we can use division. So we start out with an integral That looks like that. This. Now here we use integration or division. Let's say we have x plus 3 into x plus 1. So we say 1 goes into it one time, so we have x plus 3, and that's subtracted from x plus 1, so that's minus 2. So we have 1 minus 2 over x plus 3. So that is broken up into two integrals, dx minus 2 dx over x plus 3. And then we use a u substitution. U equals x plus 3 du equals dx. And we have dx minus 2 du on u, and that is x minus 2 natural log of u, and then we substitute back in the x. So we got x minus 2 ln x plus 3. But we also know that that's a square, so we got x minus ln x plus 3 squared. And so we have now our answer. We go, this is x plus 1, x plus 3 dx equals x minus natural log of x plus 3 squared plus c. We can't forget the constants. So here is our final solution. And that does that. So far we've seen u substitutions, division, and trigonometric substitutions. So we've already used 3 different methodologies. Now, our next one is going to make use of partial fractions. Now, we could do it another way, but we'll use partial fractions. So let's try this one 2 different ways. We're going to try, we got dx on x squared minus 4. So we have 1 on x squared minus 4 equals a on x plus 2 plus b on x minus 2. We have 1 equals a x minus 2 plus b x plus 2. And now we set x equals 2 to solve for b. So we have 1 equals b times 4. So b equals 1/4. We plug that back in, and we got 1 equals a times x minus 2 plus 1/4 times x plus 2. And here, let's say x equals 0. And we have 1 equals a times minus 2 plus 1/4 times 2. So we got 1/2 equals a times minus 2, a equals minus 1/4. So we have now two integrals equals 1/4 dx over x minus 2 minus 1/4 dx on x plus 2. And now we do a simple u substitution where we say u equals x minus 2 du equals dx, p equals x plus 2, dp equals dx. So we put these in, and we've got our usual form. And now we have, whoops, gotta get that straight. We have 1/4 natural log of u minus 1/4 natural log of p plus c. But we can use our rules for exponents and logarithms, and we've got equals 1/4 ln of u on p plus c, and that is 1/4 ln, and we plug in our values, x minus 2 over x plus 2 plus c, and then we can do other things. We could leave it this way. I think in my final solution I left it this way. Or you could recognize that 1/4 equals 1/2 times 1/2, and we could bring that in. We could do this, or we could go ln for x minus 2 over x plus 2 plus c. And that would be dx over x squared minus 4. And that's one solution. Or we could use a completely different method in trigonometric substitutions and go right to it from a trig point of view. So here, remember what this is. We can take a look at that from a different perspective. We have dx what was our problem? X squared minus 4. Well, remember we got cosine squared theta plus sine squared theta equals 1. We have 1 plus tangent squared theta equals secant squared theta. And tangent squared theta is equal to secant squared theta minus 1. And that's sort of the form we have right now. So we say that x equals 2 secant theta, and dx equals 2 secant theta tan theta d theta. And we then substitute that in, and we have 2 secant theta tan theta d theta over 4 secant squared theta minus 4. And then we can bring out the 2 and the 4, so we got 1/2. We recognize that secant squared theta minus 1 is tangent squared, so we have secant squared theta tan theta d theta. Whoops, I don't know why I did that. That's secant theta. And that's over tangent squared theta. So we have now 1/2 secant theta d theta on tangent theta. Well, secant theta is 1 over cosine theta, and 1 over tangent theta is cotangent, so we have cosine theta on sine theta. And we have 1/2 d theta over sine theta, and that's equal to 1/2 cosecant theta d theta. And now we got a little bit of work here to do. We will have to, you see, sometimes while a method works, it isn't necessarily the easiest way to go. Now we're going to have to think about this. We have if we divide by sine, we have cotangent squared theta plus 1 equals cosecant squared theta. And if we have y equals cotangent theta, we have dy equals cosecant squared theta d theta. I think that's a minus sign. Let's work this one out just to make sure. I don't want to just arbitrarily put a result down without first, let's see, and that's equal to cosine theta over sine theta. So this is y equals sine 1 theta cos theta. And we have dy equals, now this is minus sine theta over sine theta, and minus sine squared theta over cosine squared theta, and that is equal to minus 1 plus cotangent squared theta, and that's equal to minus cosecant squared theta d theta. So we had that right. I just wanted to make sure. But then when we take the integral, that just tells us we got cotangent theta let's look. Yeah, that is cotangent theta equals cosecant squared theta d theta. That's not going to help us any. Multiply that by 1/2 cosecant theta d theta, but we want to, let's multiply by cotangent theta squared plus 1 d theta, and then we have 1/2 and that's over cotangent squared theta plus 1. So we have cosecant theta cotangent squared theta on cotangent squared theta plus 1 d theta plus cosecant theta d theta on cotangent squared theta plus 1. Okay. That then leaves us with 1/2 cotangent squared theta on cosecant theta d theta plus cosecant theta on cosecant theta d theta squared these have to have 1/2 there. And let's see where that brings us. I'm not sure that brings us anywhere. That's something that I'm going to have to, well, I'm not sure I used the right trigonometric substitution here. Let's see. We could have done it this way. We could have done it this way. Let's look at it this way. dx on x squared minus 4, and that's equal to minus dx on 4 minus x squared. And then we say x equals 2 sine theta, and dx equals 2 cos theta d theta. And then let's see what this does. Minus, we have 2 cos theta d theta on 4 minus 4 sine squared theta. We bring out the 4. 2 and the 4 equals minus 2 on 4 cos theta d theta on 1 minus sine squared theta and we have cosine squared theta equals 1 minus sine squared theta. So then we have say secant that will end up being a secant theta d theta. And now we have a trick that we can do for the secant of theta. Just a minute. Here we go. So we've got secant theta d theta. Okay, so what we do here, darn, I keep switching this. So let's multiply the numerator and the denominator by -1/2 secant theta times tangent theta plus secant theta over tangent theta plus secant theta d theta. Okay, and now we break it up into two parts. -1/2 secant theta tangent theta d theta -1/2 I'm sorry, forgot this, tangent theta plus secant theta, and secant squared theta over tangent theta plus secant theta d theta. Okay. We've got, ooh, darn it. You know what we do? I gotta get in a more comfortable position. You know what we do? I made a mistake by separating the two. I shouldn't have separated the two. So what we do is we leave it under one integrand. We got secant theta tangent theta plus secant squared theta d theta on tangent theta plus secant theta. Now we use a u substitution. U equals tangent theta plus secant theta d, and then du equals secant squared theta plus secant theta d theta tan theta d theta. And that's what we have in the denominator. So we have du over u, and that's equal to minus ln u, and then we substitute back in for u. Secant theta plus tangent theta plus c. And then we could we can then we could take the square root. We can leave it like this. And this could be our answer for this particular problem. And then we've got a different solution for the same problem. So we compare the two answers. Whoops. We compare the two answers. Let's look at this. Answer. You see how I'm glad we worked it out this way, because you see, you can get yourself into a tangle if you don't choose the right method. So let's look at the answers. I think that was nope, that's not the right one. I have difficult time seeing the projects. Maybe this is it. Yep, that's it. We had, now it's a natural log, but we have the ratio of x minus 2 over x plus 2, whereas with the other, we had a natural log, but we have trigonometric functions in the argument. So it'd be interesting to compare and see if they're equivalent. But the two different methods yield two different results. And that's sometimes why when you go to a table of integrals, you'll find the same integrand with a different answer than what you've worked out. And that's an important point, because you can have different answers, something that looks totally different, and yet from your answer, but they're equivalent, they're the same. So that's it just depends on the technique you use. So here we go. Now this one I think is pretty cool. This one is really neat. Now pay close attention to this. This is where we have, let's say, an integral y equals tangent to the n of x dx. Okay? So in order to do this, we can split this out using the law of exponents. We can say tangent x to the n minus 2 tangent squared x dx. And then tangent squared, we know, is equal to 1, or, sorry, is equal to secant squared x minus 1. So then we have tangent to n minus 2 x dx. Whoops, let's not get the dx yet. times, whoops. All right. Secant squared x minus 1 dx. And then we can split this up. Tangent n minus 2x dx. Whoops, I keep jumping ahead. I shouldn't do that. Secant squared x dx minus tangent n minus 2x dx. All right, so this can be solved. U equals tangent n minus 2, or let's say just tangent x. So let's erase that. And we go tangent x. Du equals secant squared x dx. So that's u to the n minus 2 du minus tangent n minus 2 x dx. Now, we just use our regular polynomial formula, and that's u to the n minus 1 on n minus 1 minus tangent of n minus 2 x dx. And then we substitute back in, and that's tangent n minus 1 of x over n minus 1. And we have tangent n minus 2 x dx. So we have this formula, tangent n of x equals tangent n minus 1 of x on n minus 1 minus the integral of tangent n minus 2 of x dx. Now, what's so interesting about this is we can use this and create a table for any power of n. The exact solution for the tangent x dx. Whoops, I gotta make this correct. I forget the dx sometimes. Can't do that. So this is pretty cool. Now, what we're going to do is we're going to create a table. Now, this gives you almost like an infinite number of, literally an infinite number of integrals that you can solve that involve the tangent. So, tangent, well, first off, darn it. I don't know why that does that. I must be hitting something. Okay. Now, let's create a table. We're going to go n. And we've got this formula, tangent n of x dx equals tangent n minus 1. Oh, let's write that more clearly. Okay. Minus 1 of x over n minus 1 minus tangent n minus 2 of x dx. So we're going to use that. And first off, we're going to notice that n is 0. Anything to the 0th power is 1, so we have dx, and that's equal to x plus c. Okay. Now, we left off at, let's see where my pen is. Okay, we left off at using this formula up here that we derived to create a table of integrals. And so when tangent of n and n is 0, we just have dx. And anything to the 0th power is 1, so we have dx, and the integral then is x plus c. When n is 1, we have tangent x dx, and that is equal to tangent to the 0. Let's see. When n is 1, we have sine x over cosine x dx, and u equals sine x du equals, or let's say, let's bring that back again. This is cosine x. Let's say u is cos x, du equals sine x dx. So we end up with u du over u, which is ln cosine of x plus c. And you got to put a negative sign there because this is a minus. So we have that. Now we go to n is 2. So we have tangent squared x dx, and that's equal to tangent x plus, now this would be tangent to the 0 x dx, but we have that already, so that's tangent x plus, or minus, I'm sorry, this is going to be a minus sign here, minus, and that's going to be minus x plus c. And then we go to 3, and that is tangent to the third x dx, and using our formula we have, tangent, let's see, we have tangent squared x over 2 minus tangent x dx, but that is equal to tangent squared x over 2 minus ln, so that's plus ln cos x plus c. And we can continue on over and over indefinitely. Tangent to the fourth x dx is equal to tangent to the third x on 3 minus tangent squared of x dx. But remember, tangent squared was this value over here, so that's equal to tangent to the third x over 3 minus tangent x plus x plus c. And we can go on. We could build this table to infinity. Tangent to the fifth x dx equals tangent to the fourth x on 4 minus tangent to the third x dx, and we have that solved. That's equal to tangent to the fourth x on 4 minus tangent squared x on 2 plus or minus ln x ln cosine of x plus c. And we just can go on. We could build this table on indefinitely using that formula. And that's a pretty cool way of finding these integrals. So whenever you're faced with that, all you have to do is work out this one formula, and it will allow you to find the integral, the solution to the integral for any power of tangent of x. And I think that's pretty wild. So that is an amazing result. And we had looked at the secant of x. We can do the same thing for the cosecant of x. Well, I don't know why I did that. We'll close this. We've already seen the integral for the secant of x. That was a pretty neat trick. Now we're going to take a look at y equals cosecant of x dx and we're going to use the same trick where we multiply cosecant of x by cosecant of x plus cotangent of x cosecant of x plus cotangent of x dx, and we have then cosecant squared of x plus cosecant of x cotangent of x on cosecant of x plus cotangent of x dx. And then all we have to do is use our u du substitution. So we say u equals cosecant of x plus cotangent of x, and du equals minus cosecant of x cotangent x minus cotangent, or cosecant, I'm sorry, cosecant of x squared dx.
Well, that's the kind of
and now
that we ought to perform.
We have a minus du on u, which is our familiar form, which is minus ln of u, and then our final answer is minus ln cosecant of x plus cotangent of x plus c. And so, like the secant of x, we do a very similar trick to find the integral for the cosecant of x dx. And with this, I think we've done enough integrating for now. There's only so much we can do, and keep our minds from becoming jaded.